And I have Anusha Alfi-Khound with me, and we will be hosting the webinar on behalf of Conexsym Global. Our knowledge partner for this webinar is National Environmental Engineering Research Institute, NEERI. Just to go over a few last-minute items, we are recording the webinar, and we will be providing both the recording and a copy of the presentation to you upon completion of the webinar via email. And we do want to encourage you to send us any questions that you have throughout the webinar via our chat window. Our presenters will work to answer any questions that you have during our Q&A, which will be at the end of the webinar. So feel free to send any questions that you have. And additionally, please feel free to share any comments, feedback, and questions that you have with info@conexsym.com.
It is now my pleasure to introduce our presenters to the webinar. I would like to introduce our first presenter, Mr. Sukhmeet Singh. He is the CEO and founder of a bioenergy company known as A2P Energy, majorly involved in solving the huge problem of paddy straw burning in North India, which causes severe air pollution everywhere. Every year. A2P Energy is setting up bioenergy plants in Punjab for converting paddy straw into energy products. A2P Energy actively works with Aston University, UK, and European Bioenergy Research Institute for bioenergy tech transfer. Our second presenter is Dr. R. Vinu, who is currently an associate professor in Chemical Engineering Department at IIT Madras, Chennai. He has a PhD in Chemical Engineering from Indian Institute of Science, Bangalore. Prior to joining IIT Madras, he was a postdoctoral researcher in the Department of Chemical and Biological Engineering at Northwestern University, USA, where he was involved in the US DOE's National Advanced Biofuels Consortium project on kinetic modeling of biomass pyrolysis. Now it is now time to pass over to Mr. Sukhmeet Singh and Dr. R. Vinu.
Thank you for the introductions. Should I go first or how's?
Yes.
I think you go first, Sukhmeet.
Okay. So yeah, so thank you for the introductions. I'll just share the presentation. Can you enable the presentation for me? It says host disabled. I need presenting rights.
Yeah, sure. It's done.
Yeah. Are you able to see the screen?
Yes.
Okay. So yeah, hello everybody again. I'm Sukhmeet. I'm the founder of A2P Energy. It's a biofuels company as of now focused towards North India, majorly working on paddy straw management and biofuels from paddy straw. So I'll take you to what we will be discussing today. Problem of paddy straw, briefly, technology-based solutions, what we work on, advanced biofuels, some of the work which we are doing right now, online intervention, also where we are working on a platform for paddy straw exchange, buy and sell, and overall about our team and impact. Coming to I think the problem, so we most likely would be knowing about the whole smog problem in North India. 35 million tons of straw is there. When we started the company, focus was how do we prevent this pollution, and health was one of the major focus, as it keeps on affecting the general population in North India. And on the other hand, the economic problem of the farmers, where farmers are doing suicides. So we thought, why not farmers should be able to generate income out of this. This is the air pollution, probably you can say the map, the killer map of air pollution. 6.5 million people are dying because of air pollution, and India is one of the major, or I guess the biggest country which is getting affected because of the air pollution. And we have 14 out of the world's 15 most polluted cities in India. Coming to why particularly the paddy straw gets burned, there are few things which we know, and few things which from a farmer's perspective are very important. So we know that okay, there is less time between two cropping cycles, high cost of machinery. Also, the last thing which is not discussed too much is there are actually the users and the buyers of the straw, but there is no organized way to actually exchange straw. So even if as a farmer, individual farmer in India would own, let's say, 10 acres of field, it will give approximately 1 acre gives 2 tons of straw, so it will give 20 tons of straw, which can come out from that particular field. Now there are one side some users which can use straw like mushroom growers or vermicompost people or even for fuel, but there is no organized channel actually to tie this up. We've been also discussing about the COVID impact. This is a very worrisome situation going to happen. Recent study mentioned about air pollution may increase the risk of COVID death. So as of now, I think one of the biggest things, or one of the major things government is talking about, that our recovery rates are very good, but the impact of air pollution on COVID is going to be worsen the impact of the air pollution on the deaths happening in North India specifically. Now coming to the technology-based solutions, what we work, and specifically the product line. So we, when we started from a supply chain perspective, we made a online model to identify straw. Once it was collected, we realized that the cost of collection is too high to actually use or transport it further for other industrial purposes. So the second year, we realized that we have to reduce the cost of collection. Cost of collection is like when you can't go to distributed fields and start collecting straw because the machinery for collection is big. So you need to have the planning done beforehand. And the only way you can do it is through satellite images. So we made a model which identifies paddy straw before it's harvested. Like when the rice is growing, we can identify where all rice is growing. The model color codes it in terms of black and gives us the area for that, for where paddy is being grown. And then we work with farmer entrepreneurs to collect that. So once we collect the straw, then we process that into different biofuels. I'll talk about that. And then some of these are first generation biofuels, some are second generation. And these are basically, our target is to replace the fossil fuel in the industry and the power plants with this green biofuel. So this is our range of products. So on the left-hand side, straw is a fuel where we work as a supply chain partner to supply or collect the straw and then supply it throughout the year. Then we also have these hard fuels for boilers, briquettes and pellets, which can replace either wood and coal in the boilers. And then we have on the right-hand side fuel specifically targeting higher value product like coal, oil, and directly gas and electricity. So some of this work we are scaling this up. Some work is already commercialized. So I'll discuss more about these also in the coming slides. So we started in 2018. So we have 4 installations. We did 2 in 2018, 2019, and 2020 each plant in these years. So some, as I mentioned, focuses on brown or the fuel specifically for boilers, and some we are focusing on bigger power plants to supply to replace coal. So some of the pictures at the bottom of our systems. So this I discussed about the AI model. So it's a basically automated identification of straw, so what we do is during straw collection, the time is so less. So we work with farmers and farmer entrepreneurs who have machinery for collection. So what we do is we identify the area and tell them where we want to go and collect. So once we started using the model, the idea is to not go to distributed smaller fields, but continuous fields where the collection can be efficient. So we go to this continuous fields and collect the straw. So it helps us reduce the cost by around 12% or so. This is also the first line which we made was to make the hard fuel, specifically the pellets. So we made this indigenous production line for producing pellets. So there is a lot of silica in straw. It causes a lot of wear and tear, which metallurgy to use, what process to use. So we have designed the most of the machinery here within our team and then got it manufactured. So the idea is to take out the not so good components in straw so that it can be used as effective fuel. So both from the process perspective and the metallurgy perspective, we research a lot. And Aston University, European Bioenergy Research Institute has been our partners since inception, and we work closely with WWF, PAU, and Indian Institute of Petroleum, and some work with Dr. Vinu also on our biofuels part. Now coming to advanced biofuels, so we are working on a few projects specifically on oil, gas, and the coal part. So we have a couple of reactors for producing oil out of straw. These are more R&D scale reactors, but as of now, the idea is to have it more distributed reactors in rural areas. So we are also starting. So once the oil comes out and the gas comes out from these reactors, can be so the main one of the biggest issue is about distillation of these oils and gas so that it can run on conventional engines, both gas and oil. So that part we are still working on, but as of now we were successful in taking out oil and gas from these reactors. This is our plant for taking out paddy straw to biochar. Biochar can be used as a soil conditioner and also coal replacements. So what we have done is this also we have now scaled. So it was an R&D project first, but now we have set up an industrial unit for that. And recently we've won a government tender to actually replace coal in the power plants using our green coal, which we make out of paddy straw. The one use is as a fuel, and second use is as a fertilizer for soil enhancement. This is so I did mention about an online platform. What is happening is we see that there are companies which want to come and establish plants based on the raw material is paddy straw, but they worry about getting the straw in a very structured form from multiple farmers. Since the land holding is small, so interacting with so many farmers becomes really a tough job. So what we are building is a platform where it's a market making platform for matching supply and demand, reporting farm fires. So that is what currently we are building. It's a platform which will report farm fires, do match supply demand for paddy straw, and also we are integrating some IoT components to actually see what is the result of the intervention. If it is has been an intervention has been done in a on the ground for taking out straw instead of burning it, we see what is the impact in terms of less pollution, less emissions from those villages. We also work with some of the corporates to, so we have a not-for-profit arm where we work with employee giving, corporate CSR, and some of the R&D projects. So this is, we have worked with companies like L&T, Cisco. We're currently talking to a few more to sponsor either through their CSR initiatives, where they sponsor, let's suppose 500 to 1,000 acres of land, where we say, okay, you help us buy that straw, and then we utilize the straw in multiple ways. The money from the corporate CSR goes to the farmer, power entrepreneurs for collection. Once this cycle is started, it's a auto cycle which can continue, but one-time funding infusion happens through the corporate thing. Also through employee giving, we are exploring if one employee can sponsor 1 acre. It only costs 3,000 rupees to sponsor 1 acre. So that money goes to the farmer entrepreneur. We take straw from them instead of letting them burn, and then we work with the industrial partners to utilize the straw. So some of the pictures of our operations, you can see the stacked straw. So there are challenges in terms of because this is a raw material which is available probably a month's time in a year. There is also a challenge in terms of storing it throughout the year, because once you start producing fuel out of that, you can't say to the customers that you can only supply for a few months in a year. So what we have to do is to store it for the complete year and then process it slowly. So this particular, so there is an art to also store the straw to prevent the damage. So what we have done is also from a fire prevention perspective, there has to be measures which have to be taken when we store the straw. So again, learning from a supply chain perspective has been a critical component when we work with the paddy straw. So we also see the impact for our manufacturing plant in terms of fossil fuel, employment generation, income generation, amount of air pollution which is saved from. So this is what we've come up with is a distributed kind of processing and storage rather than a bigger, huge plants. So we have seen that the distributed way of storing and utilizing straw has been successful. We've seen some of the bigger plants getting failed because the size becomes huge, and then the supply chain cost for straw also increases. So that's the thing. So we've come up with this hub and spoke kind of a model. The storage can happen in these distributed hubs, and the processing can either be done in a collective way, or even the processing can also become in a distributed manner. We are expanding in terms of number of our processing plants, and also I mentioned about the next generation fuels of coal, char, gasification. So this is some of the work that we are doing in the R&D space. So this is our team. I run this organization as CEO. Dr. Robert Berry has been in the organization from starting, and few other people. My background has been both academic. So I worked in ISB, Indian School of Business, for 7 years. Before that, technology background. So mix of academics and R&D and technology. So in 2018, I started this. Dr. Robert Berry has been working on paddy straw as a research project for last more than 10 years, utilizing straw for energy purpose. So he was working at Aston University and European Bioenergy Research Institute, and some of the other team members I've mentioned. Apart from that, we have team manufacturing units. So we've got good retention, warms on awards from likes from UN, WWF. We are winners of Global Maker Challenge, which happened last year in Russia. We were also awarded by United Nations as air pollution winners for 2020. And partners I've mentioned about that earlier. I think that's it from my side. Thank you.
Should I get started with my presentation?
Yes, you can start.
Okay. Can you enable me to share my screen?
Mr. Singh, you are the host. Can you enable the share screen option for Dr. Vinu? You can make him the host.
Okay.
Thank you.
Yeah.
I hope you're able to see my screen.
Yes, we can see your screen.
Okay. Okay. So thanks for the invitation to present in this forum. So I'll be talking on novel waste to energy and fuel technologies for solid waste management in the Indian context. So I work in Department of Chemical Engineering, and I'm also a part of what is called as the National Center for Combustion Research and Development at IIT Madras. So just like just to extend on what Sukhmeet had already presented, so I'll probably try to expand on the type of waste that we are really confronting today. In addition to paddy straw, we also are really facing a huge solid waste management problem due to the municipal solid waste. So that will be one of my important topics: single-use plastics and rice straw. So I come from an academic background. So I will, and we are also working towards really scaling up our technologies to the market. So there are like currently two technologies that we are working on. One is a pyrolysis or a co-pyrolysis technology, and then the other one is a hydrothermal liquefaction technology, which I'll be addressing in the next few minutes. Okay. So the primary research focus of my research team here at IIT Madras is to really look at a variety of these processes to convert, of renewable as well as non-renewable feedstocks to energy, biofuels, chemicals, and other value-added products. Okay. So you can see here that we deal with, municipal solid waste, coal, polymers, plastics, biomass, and we adopt a wide variety of
Okay, now. I'm sorry, there is some issue with the connection from Dr. Vinu's side, so we lost him right now, but we'll try to get him connected back.
Hello.
Yes,
I'm sorry. I think I got disconnected and I've just got reconnected.
that's okay. So, yes, Dr. Vinu is back here, and you
Shall
can
I?
continue.
Okay, fine.
Thank you.
Okay, let me continue. I'm sorry. I think I got disconnected because of poor internet. I just switched to Geo. Fine. So I think I was at this slide when I got disconnected. So so there are a wide variety of agro residues in India, right? And you know, as Sukhmeet pointed out, right? I mean, there is a huge amount of you know, rice straw, particularly in Punjab, that is being burnt, and that leads to a lot of pollutions. And apart from that, we also have a wide variety of other types of species, like what I show here as a Prosopis juliflora plant, which is actually an invasive species. And you know, there was a huge drive, for example, in Chennai a couple of years back to really cut it down, because it has a lot of it actually you know, it actually takes up a lot of groundwater. So we have a wide variety of these agro residues which can actually be utilized for biofuels, both solid as well as liquid biofuels. And essentially, you know, by open field burning, we are really losing a lot of nutrients. So there has to be a way by which you really recycle the nutrients back to the ground, or we typically use them for other applications so that we essentially maintain a circularity. Okay. Coming to the other side of the story, right? We also deal with you know, a lot of the solid waste management, which is really mounting to a great problem. So so again, this is also a very important thing that everyone would know, that the typical you know, the Ghazipur East Delhi garbage mountain has is really crossing the height of Qutub Minar. It's a very popular images that you can see. What is more important is, unlike MSW of the Western origin, Indian MSW is highly heterogeneous and complex because its moisture content is very high and its calorific value is going to be very low. So, and again, you cannot really think of segregating huge amounts of these MSW for processing them as, you know, plastic separately and bioorganic separately and so on. So there has to be a way by which we really, or we develop some kind of a technology which can really take everything, irrespective of what it really contains. And this has been one of the key research drives for us to invest in technologies that can take up, you know, that is essentially feedstock agnostic and can actually take up any type of feedstock. So this is a typical waste profile, you know, from Trichy municipality in Tamil Nadu. So you can see that, you know, a municipal solid waste is really composed of, you know, wide variety of components, including kitchen waste, garden waste, paper, plastics, right, and many other things. And it really varies based on the place, and it also varies based on the time. Okay, it varies spatio-temporally. So it's very important to understand what I mean, what ways by which we can really convert these MSW to energy and fuels. And the other big problem that we all know is the single-use plastics that has come up. And now recently with the COVID times, right, we also have a lot of these PPEs and these kind of one-time use plastics that are being dumped up in the dump sites. So as you can see here, packaging accounts for the major utilization of the plastics. And as you can see, this is the UN report, a very excellent report on single-use plastics, if anyone is interested. So that gives you an idea of what are all the different types of plastics that are actually there in the dump site. So typically, you know, LDP, HDP, polystyrene, PET, polypropylene, and expanded polystyrene, right? And all these, you know, have really replaced the previous packaging material, which includes glass, paper, jute, and metal. So again, this forms a very important component. You know, 8 to 10% of the solid waste in the MSW is composed of these kind of single-use plastics. So we are actually talking about a paradigm shift in the solid waste management. Okay, so earlier days, what was essentially thought is we typically, you know, source reduction was actually given a very low priority, right? So typically we end up landfilling all these wastes, right? Then we look at conversion technologies, recycle and composting, and finally, right, source reduction was given a least priority. But now the paradigm shift for the 21st century is that we first look at source reduction, right? Recycling, composting, conversion technologies, and landfilling. And one of the reasons that, we focus very less on landfilling is also because the landfills have almost become dump sites, right? And we are not properly landfilling the areas. So in that context, right, the conversion technologies, recycling, composting get a very, very high priority. And in looking at all these, what is very important is we have to really see if we are actually generating energy or fuels from waste, or essentially what we generate is a waste. Okay, because it is very important to understand that the energy generated from these waste, right, should be greater than the energy that it is consumed in the whole process of this conversion, right? So as an example, right, if more amount of petrol or diesel is going to be used up for moving the garbage from garbage in the trucks, right, than the energy that we finally get out of it, then the net process is a waste. Okay, so this is a very important thing that really comes down to the the waste, the efficient design of efficient processes, right? I'll touch upon a very important aspect of rice straw. Sukhmeet rightly pointed out that you can actually convert rice straw to biochar or the rice straw char, and actually you can use them for burning in the combustion plants, right? It is actually efficient, and it is in fact the right way to really consume huge amounts of rice straw and get rid of such high volumes. But there is an issue with respect to combustion of rice straw, right? So one of the important aspects is because rice straw contains significant amount of ash, or the we call it inorganic components, right? It leads to a lot of these bed ash and unburns that are formed, right? And it leads to a lot of slagging and low heat transfer efficiency in the furnace. Essentially, these are deposits of these metal ions or oxides in the furnace area, right? You can also expect fouling of superheated tubes, which means your OPEX is going to be higher, and corrosion of tubes. That means you're actually losing a lot of these lot of capex, and that's primarily because, as you can see, some of these small reactions that I have mentioned here, right? So rice straw contains a lot of these silica, potassium, and chlorides, right, which can really really harm the boiler that is actually converting it to energy, right? So if you simply compare the composition variability of rice straw with other types of agro residues, you will see that potassium and chloride are significant in rice straw compared to any other type of feedstock, and that results in a wide variety of these different reactions or complex salt formation, which leads to the capex and opex issues. Okay. So when we really look at how we can convert be it biomass or plastic to energy and fuels, right? So this is a slide which essentially tells you how we convert it to fuels, right? So this is called as a Van Krevelen diagram for those that do not know about this. So this is a plot of hydrogen to carbon in the feedstock to oxygen and carbon in the feedstock. I don't want to go more into the technical aspects, but what is important to understand is, all these biomasses, agro residues, stubbles, all contain significant amount of oxygen in them. And if you want to now convert them to gasoline, kerosene, or diesel, any of these transportation grade fuels, right, you have to really significantly decrease the amount of your oxygen in the feedstock, right? And to do this, there are like different processes that are available, right? You do hydrogenation, hydrodeoxygenation, deoxygenation, and stuff like that. So essentially you move from this point all the way to this point here, right, to make gasoline, kerosene, and diesel, right? So this is typically done in the refinery. It can be done in the refinery, but still it is also a challenge for the refinery to really take up this, because you need to supply significant amount of hydrogen to convert these the oxygen that is present in the biomass in the form of water, right? So we actually was thinking if we can really mix these biomass and polymers, because we know that these polymers, what we are talking about, polyethylene, polypropylene, polystyrene, are all hydrogen rich. Can we really blend them with oxygen rich biomass and then try to have this effect of hydrogenation by simple mixing of these? And this is also one of the ways by which we can treat the real municipal solid waste, because that anyway contains biomass, plastics, and all other contaminants mixed together. So this was our original thought. In fact, we did a lot of these lab scale experiments. I'll probably not spend too much time on it, right? We actually start off with micro scale experiment just to verify if what we think as a concept will really work. And so we have some of these analytical facilities using which we, so in one of the studies, what we did was, we mixed the cellulose and polypropylene, right? Cellulose as a biomass and polypropylene as a polymer, right? You mix them together and then we understand what is the typical calorific value or the higher heating value of the pyrolysis vapors. And we found that, right, when we are going to mix these two different components, we do get significant amount of significant calorific value. You can see that this is much higher than what we are thinking about cellulose, whose calorific value is only 22, right? So we can get closer to the calorific value of the of the final fuel or the transportation grade fuel, by mixing these. And why this happens, I mean, there are a lot of postulates and reactions that one can say, but essentially what you can see here is you can actually find out that you actually produce a lot of these long chain hydrocarbons, okay, or hydrocarbon alcohols in this process, and that really results in significant calorific value of your final oil. Okay, so we are talking about liquid fuel here. So we actually verified this in the lab at small scales, right? But that is not enough, right? So we actually go to a large scale and try to do I wouldn't call this as a bigger pilot, but probably a smaller pilot at the rate of 2 kilograms of feed processing per hour to convert the waste biomass and polymer mixtures to value-added fuels, right? So we actually developed this with a grant from Gale. We developed this microwave reactor with catalytic upgradation. Why microwaves? That is shown here. Right, so in microwave, you can actually have a very good or uniform heating of the material in a very, very short period of time, because this is a radiation-based heating, unlike conventional heating, which goes by conduction, convection, and radiation. So it's an electromagnetic heating, so it's more of an energy transfer that occurs as opposed to heat transfer. So we actually performed multiple experiments, with rice straw, bagasse, okay, polypropylene and polystyrene, right? Commercial samples, mix them together, and then see what is the final quality of the product, right? I'm probably giving the final numbers. So what happens is, right, we heat the material over here, right? And then we pass it through a catalyst tube, right? Where the catalyst essentially helps in upgrading the quality of the product. And finally, we condense the oil. Right, and in this process, we found that as we optimize the catalyst loading, right, we can actually decrease the viscosity of the oil from very high viscosity to something which is of the order of 1 to 2, which is same as that for light fuel oil. Right, we can also bring down the density from 0.9 to 0.85, which is very similar to the gasoline range, and we also bring down the flash point, right, from 98 to 72. And for all the different types of biomass plus plastic mixtures, you can see here that we have achieved the density which is very similar to the light fuel oil, right? And we have also achieved the flash points which are similar, and calorific values are also very, very much equivalent or even higher than the conventional fuel oils. So by this, we actually demonstrated that this kind of mixing, a hydrogen-rich feedstock with a oxygen-rich biomass can actually lead to a much better quality oil, right? And we have also done a few tests with ocean plastic waste and also some kind of masks and these kind of single-use oven fabric waste and also municipal solid waste. Okay, I'll probably take like 3 minutes to just explain the next part, right? So this is about pyrolysis, right, which is typically a high temperature process. And if your feedstock is going to contain significant amount of moisture, that is not really the process to go, because you need to spend too much amount of energy to dry the feedstock before you subject it to high temperatures. So another technology that we are currently working on through one of our incubated startups is called as a hydrothermal liquefaction, which is more like mimicking nature's method of producing fossil fuels by applying high pressure. So typically, we operate at temperatures around 300, right? and high pressures where water attains the density of an organic compound, right? So all in all, we have a high pressure cooker. You can call it simply as a high pressure cooker, right? And we feed the feedstock, right? We operate at, typically for 1 hour at high pressures, and we get what is called as a crude. And this crude has much better properties than pyrolysis oil, and that can also be easily or seamlessly integrated with the refinery infrastructure. And we have carried out a lot of these tests with real MSW, which is collected from the downsides in Chennai. And I mean, in a small reactor, and we had typically 58% of oil with very high calorific value, right? Overall, more importantly, right, we really did a mass and energy balance analysis of the process and found that I mean, the process is overall energy positive, because the energy of the products is much higher than the energy of the feed and the heat that is really supplied. Because it's a high pressure process, you don't need to supply significant amount of heat energy, right? So we have really tested it for a wide variety of feedstocks, including, as you can see here, rice straw with some kind of solvents, bagasse, right, municipal solid waste, right, defatted yeast. We are also now focusing more on ocean biomasses like seaweeds, which are actually having very high potential to produce biocrudes and biochar, right? So we are essentially expanding the feedstock range. And I mean, through the startup X2 Fuels and Energy, which is an incubated startup at IIT Madras, we are trying to really bring in a lot of these process integrations in order to have the final market price, selling price of our biocrude and biochar to be competitive with the typical market selling price of these products. Okay. And again, I'll not go deep. There are a lot of applications, because we can typically blend this biocrude with crude oil. It can be fractionated. It can be seamlessly integrated with the refinery infrastructure. It's a very good source for bioplastics and biolubricants. And it can, I mean, the most simplest application is you can simply blend it with furnace oil for use as fuel oil applications in in stationary heating source applications. Okay, so I would like to conclude that what I essentially presented is co-pyrolysis of biomass agri residues with plastics. So this is a very good strategy, is what we found. We are trying to really expand this to a wide variety of waste, including COVID-related waste, so that we can improve the quality of the products. HTL is something that we are really working at a pilot scale. We are trying to build 100-liter and 1,000-liter reactors. So what we have done so far is more in the 1-liter batch, and we have now developed and doing these trials in 100-liter and 1,000-liter reactors, which can be suited more for distributed applications. And finally, a continuous is something which is typically 2 years down the line, where we are trying to develop a much larger scale version for treating municipal solid waste in the landfills. So I would like to conclude, and that's more of my personal opinion, that to address the grand challenge of solid waste and stubble management, right, it's very important that we look at multiple technologies and not really think about one, and that too in a more centralized as well as distributed manner, so that we can really address the scale issue and also the overall techno-economics of the process. So acknowledge my students who have been of great support in a lot of these works, and my collaborator Satya of aerospace engineering. And some of our projects are being funded mostly by the industry. We get a lot of support from industry for biofuels and biomass and plastic waste conversion projects. So with this, I really thank you. I again apologize for the intermittent break in the beginning of my talk. And if there are any questions, I'll be happy to take.
Thank you so much, Dr. Vinu and Mr. Sukhmeet Singh. Thank you so much for your insights today. And we have a few questions that came through during the webinar, and we would like to put it up first. The first question came from Dr. S.K. Goyal from NIRI, and he has a question about the characteristics of fuel made. The answer has been already given. However, I would like to I would want to ask Dr. I would like to know if Mr. Sukhmeet Singh would like to elaborate on the answer.
Yeah, so thank you for the question, Koel. You mentioned about the characteristics. So yeah, so CV is around calorific value is around 3,500, ash is approximately 12-13%, moisture less than 10%. So I think yeah, so it can easily work as a fuel for boilers. What we do is in the process we try to take out at least the external whatever sand which is attached during the straw collection through cyclone separation, and also that the fuel, at least the external silica causing factors are removed. Rest, whatever silica is there in the straw, that remains. But yeah, we have been using this fuel in the boilers for last more than 2 years now in the industry. So typically, this would be boilers which ideally rotating bed, but can also be used at fixed bed boilers.
Thank you so much, Mr. Sukhmeet Singh. The next question we have is from Jeffrey Smith from WHO, and he wants to know more about wet oxidification.
Yeah, I just responded. So if the question is about the hydrothermal liquefaction technology, it is not really a wet oxidation process, but rather I would say that it is a wet pyrolysis process. Okay, so we are trying to essentially mimic the high pressure conditions at which typically crude oil is made underground over millions of years in a very short time frame in a small reactor. Okay, so so typically we can use water, or we also, in order to improve the quality of the oil and the yield of the oil, we try to mix water with some kind of solvents like glycerol, which is typically available from the biodiesel industry, right? And so it's essentially a high pressure process, and what really happens is cracking of the molecule. So essentially we try to crack the long chain polymeric and also the biomass components into smaller fragments, but we essentially employ high pressures, right? So the advantage is, the energy that is required to vaporize a molecule is essentially conserved. So that is the advantage. I hope the question is answered.
Thank you so much, Dr. Vinu. So do we have any further questions from anybody?
Okay, I think there is one more question from Jeffrey Smith. Yeah, wet oxidation doesn't require combustion. Yeah, so we are not really combusting the feedstock, right? So so again, in HTL, we are not really looking at combusting the feedstock. That means so HTL is more like an endothermic plus exothermic process. So you have some of these cracking reactions which are endothermic, and we also have certain reactions that release the heat. So you can't really call it as combustion. So so I wouldn't really compare it with exactly with wet oxidation process.
Thank you so much, Dr. Vinu. So do we have any further questions from anyone? All right. So looks like we don't have any further question. Over to Prarthana.
So we have reached the end of the webinar, and we would like to thank all our presenters for their time and insights they shared with us.
I think there is
there's one more question, yeah.
To Sukhmeet.
So there's a question for Mr. Sukhmeet Singh.
Yeah.
How do we prevent silica from becoming suspended?
Yeah, so as I said, when we make fuel out of paddy straw, what happens is a lot of also comes in the collection process. Silica is there in paddy straw as an inherent property that remains. But what we have seen is the silica, because of the sand being part of the fuel process, that creates also a lot of problem. So we've compared silica, like straw collection, process that into fuel, then versus collecting straw, and then taking out, doing separation of fine dust particles, fine sand particles from the straw, and then converting that into fuel. At least, so we, from a practical point of view, for using it a fuel, using as a fuel, we saw that there was significant difference between the pellets made out of the straw, which was not separated, of the sand particles versus which was separated. But yeah, inherent silica, I don't know if Dr. Vinu has any chemical process for that to reduce the slag, but
So yeah, I can probably answer. So the question is, is the gasification rate enough to consume more silica than would be oxidized? So so typically what happens is, at these very high combustion temperatures, right? So the silica and other ash components essentially tend to fuse. So so the silica doesn't really go to the gas phase due to combustion, but typically it really forms a molten slag, right? So in the furnace bed, so that forms a very important component of the the bottom ash of the combustion process. So so in open field burning, yeah, there will be some kind of liberation of the fine particulates of the silica, but so after combustion, yeah, so the silica is essentially going to be consumed in the form of formation of more complex chemicals with all other ash components in an open field burning.
no, so Dr. Vinu, just a follow up on that. From a boiler perspective, do you think anything can be done on the silica formation and the first photograph which you were showing? So sometimes we do see that formation in the boiler. We read from some of the research that lying can help decrease that.
Yeah.
But any experience on that?
So typically we add these additives, like there are like different types of additives, like lime. Lime is one of the additives, or even alumina sometimes can be used as an additive. What they essentially do is they try to really change the chemistry of the slag formation. Okay, so we call it as the ash fusion temperature, right? By adding some of these additives, you try to increase the ash fusion temperature so that ash does not really fuse and form a molten slag. So by that way, you can actually prevent the silica and all the other ash components, from reaching the boiler or the superheater and other boiler surfaces. Okay, you can essentially trap them in the in the solid phase, right? So that it really becomes a part of the bottom ash, right? And all these don't really fly and get stuck to the boiler surfaces and also the superheater tube surfaces. So the additives essentially play the role of that chemistry, so that much of this ash is not really released out in the form of fine particulates during the combustion process. But again, the challenge there, when we were associated with a project earlier, is that how do you really impregnate this kind of a additive along with rice straw? If you're really thinking of a 4 megawatt or a 10 megawatt biomass boiler, right? So you cannot certainly blend this this additive along with your rice straw bales, right? As they typically go to the process, right? So there has to be some kind of a mechanism by which you, on the fly, you try to mix this so that you're able to achieve the reduction of the liberation of the ash. What is the possible time to scaling of these technologies for commercial purpose? So as far as the pyrolysis is concerned, it is more on a pilot scale. In fact, pyrolysis of plastic is more popular than pyrolysis of biomasses, because if you really look at the West, there were a few biomass pyrolysis companies that failed. But so that is why we think that, depending only on biomass for pyrolysis to derive oil primarily. Okay, I'm talking about pyrolysis to liquids, right? So if only that is going to be focused on, then that may not yield very good benefits, because the quality of the oil is going to be poor, and we need to really spend a lot on its storage and stuff like that. So that is why we advocate the co-pyrolysis process. So we are also trying to scale up and looking for both governmental as well as industry grants to do this. But I think we are not really far, because the technology in itself is not really a new technology. So pyrolysis is a well-known process. So it's all about the challenges that we face in scale up. One, due to the variability of the feedstock, if you want to really go to scale, right? I mean, Punjab is a very unique scenario. I agree to it, because so I would say that rice straw in Punjab is like coal, right? So you have so much huge quantities of rice straw that you can really depend on a single variety of feedstock. But in other parts of the country where the wastes are highly distributed, right, you need to really have a system that can that can be readily optimized or optimized on the fly to utilize a variety of feedstocks with time. So we have used straw in Andhra. I mean, whatever studies we do are using straw from Andhra. So the quality of straw will vary. The Andhra-based rice straw is different from the Punjab-based rice straw. So they are different in terms of quality. If you really do the ash or the metal composition analysis, they are going to be different.
I think from a scaling perspective, we have been doing, we just scaled one of the technology, which is a dual phase reactor for pyrolysis. So we made it that it can be used both on biomass and plastics, and probably will be and that's an industrial scale reactor. We have scaled up to their focus is not oil, but focus is on producing biochar, which and the oil and the vapor phase we are directly burning to run the reactor. As and when we also some opportunity to from a market perspective to so that the products can be off taken, so we kind of invest in them and then scale it up. What we have seen is there's actually a stark difference between the technology availability from the West. So reactor, what we have made here, we were possible to do that in 1/5 of cost compared to reactor which we would have if we would have bought it from outside. So I think that in India we have both the availability of feedstock and the mechanical capability to produce such machines. So that reduces actually or improves the ROI on the investment. So I think all these technologies Dr. Vinu talked about, I think has a good future in India.
Yeah, I agree. So biochar is actually a very good thing to do, especially with biomasses, rather than thinking of oil production, because by biochar, you are essentially trying to make the biomass residues into an equivalent form of coal. So you have an immediate market that can really take up these biochars in the essentially in the heating and power plant industries. Yeah.
So we have come to the end of the webinar. We would also like to thank our presenters and the attendees who joined us. As a quick reminder, we will send you the webinar recording and slide deck via email. In case you would like to review anything in future, do email us at info@conexsym.com. We hope you have had a great day. Thank you.
Thank you. Thanks a lot.
Thank
Thank
you
you.
so much.
Thank you so much.
Thank you.
See you, Sukhmeet.
Yeah,
Bye.
see you. Dr. Vinu.
Should I select end meeting for all? Because I think I am the.
Yes, kindly do
Yes,
that.
please.
Okay.